Welcome. I'm Nils Reimers. I work for Hugging Face in the science team, leading the neural search and representation learning group. And this is a talk about domain adaptation for dense information retrieval without labeled data, which I will be presenting at the Language Technology Lab at the University of Cambridge. So probably you have heard about neural search and you're wondering what is the hype about neural search. So to demonstrate the power of neural search is the following. Here we have as a corpus the simple Wikipedia, which has roughly 100,000 documents. And we want to do some simple query. What is the capital of the United States? If we do standard lexical search, BM25, we see the top hits are the following. The first one is on capital, because it contains the word capital and punishment and United States. Second one is about Ohio, because Ohio is a state in the United States, it also has a capital. And the third hit is about Nevada, as it's also a state in the United States, it also has a capital. But it does not find the passage that Washington, DC is the capital of the United States. It's really low in the ranking. However, if we do the same with a neural search and an embedding approach, the first hit is about Washington, DC, which is the capital of the United States. Second entry is about what is a capital city, what does it define? And the third entry is about the Capitol in the United States. So maybe you did mistype here, and instead of you wanted to know what's the capital, you wanted to know what is the Capitol of the United States. So as you see from this simple example, neural search can be much better than lexical search. You can also put this into numbers. So this is a rather old benchmark from 2004. And we see the black line as the best system from 2004. And over the years, there have been not so much or no progress over like 10, 14 years. However, with pre-trained transformers, we see significant performance increases leading to these much better search results. One popular approach to do neural search is using Bi-Encoders. With Bi-Encoders, you encode all your documents in a dense vector space, and then you encode your query, for example, the query, what is the capital of the United States, also in your vector space. And then in the vector space, you look for the closest documents. So if your query is embedded here at this point in the vector space, you look for the closest point in the vector space. From an architecture perspective, it looks the following way. So you have some query and some document. You pass it individually through the BERT network or some other transformer network. You have some pooling operation, which takes the output from the BERT network, performs, for example, mean pooling. And then you get like some fixed size vector, which you can, for example, compare with cosine similarity or with dot product, which gives you the similarity between the query and the document. Advantages of this Bi-Encoder embedding approach is that it can overcome the lexical gap. So if you write US, USA, United States, it doesn't matter for the embedding approach. It all knows that these are synonyms. So it can overcome this issue where you search for something, but in the document, a synonym was used. It can also respect the word order. So if you want to get a visa from Germany to Canada or from Canada to Germany, this makes a difference. And a lexical approach cannot distinguish for the word order, but dense embedding approach, Bi-Encoder approach can look for the right order, for the order of the words and encode them differently. And it also knows about related terms. So for example, when you search for Spearman correlation in NumPy, maybe because there is no Spearman correlation in NumPy, but there's a function in SciPy, it will find the entry on Spearman correlation in SciPy because it knows NumPy and SciPy are quite similar and can often be used interchangeable. These embedding approaches are not limited to just text. You can also make it multi-modal. So you encode, for example, images in a vector space. Here we have the picture of two dogs. And then you can also encode different text in the vector space. And imagine you search for two dogs in the snow. It will find the respective image embedding. And of course, you can also do it multilingual, so it's not limited to one language. So if you train it on many languages, you can all map them in the vector space, and then you see which images are close to the query. Bi-encoders became really popular also in production. So for example, Baidu, Facebook, Netflix, Spotify, Amazon, they are all using dense embedding approaches for the respective search functions. And they are also especially useful for exploration. So for example, if you want to find movies that are similar to the Matrix, it's really hard if you enter this, if you say, okay, movies similar to the Matrix. But if you have some embedding approach, you can see, okay, how does the movie The Matrix look like, and what are similar movies that you could potentially enjoy. However, a big issue with Bi-encoders is the curse of unknown words. So what are unknown words? We can distinguish them into categories. First, have we seen them during pre-training? And have we seen them during fine-tuning? If we have seen them during pre-training, we have some potential, some possibility that the model still knows what is this word, so what does it represent. But if a word was not seen during pre-training and not seen during fine-tuning, it's really hard for the model to know what this word represents. The challenge is that our world is in constant change, so always new words are made up, new things are invented, things happens. So for example, here are some words that happened after BERT was created. So for example, there's XLNet. So what is XLNet? Where should we put it? If we have never seen it, you don't know. There's Cloze, which is one of the newest cryptocurrencies created. So cryptocurrencies are created like every day, but if you have never seen the word Cloze, it's really hard to know what it is. Also forward. So what is forward? So this is not a spelling mistake, but this is like a Israeli company. But if you don't know this, never have seen this word, you have no idea what this company means. Or for example, this error code OXC004F213, how should you represent this error code in a meaningful vector space if you have never seen this during pre-training or fine-tuning? So this error code is an error code from Windows you get when the activation key was not found on your machine. And people are searching for this. So they search for XLNet documentation for the cryptocurrency for this error code. And how can a Bi-encoder create like a meaningful representation for these words when it's have never seen them? And also, how does it know about synonyms? So if I talk about coronavirus, COVID-19, or SARS-CoV-2, we know that they refer all to the same thing. We can use them interchangeably. But if I search for coronavirus, how can it find documents talking about SARS-CoV-2, for example? So this is a big challenge in Bi-encoders, which is unsolved so far, and which is also part of my current research to address this issue and to find good solutions in this direction. So last year we wanted to measure how big is the impact of these unknown words. And we measured it by using zero-shot information retrieval. So idea is you train a model on some data set you have. So in our case, it was the MS-Marco data set, and then evaluate it on many other information retrieval data sets from different domains. We have from scientific publications, from medicine, from finance, from news, from Twitter. And to test a lot of different models on these 18 different data sets and to see some characteristics, which model will perform well to unseen domains, unseen tasks, and which models will fail miserably. And if we look here and compare the lexical search with BM25 to a dense embedding approach, so at that time we used the TASB, which was the best model back then. We see in domain on MS-Marco quite a big difference in terms of MDCG at 10. So we get like 18-point better performance using the dense model on the in-domain evaluation. However, if we move to more specific data sets, so BioAsk is on biomedical articles, SciDocs is on in general scientific articles, we see that the dense models have a lot of issues because it have never seen the specific terminology in these domains, so they perform quite badly. And in fact, it was that BM25 was better on 10 out of 18 data sets than the best dense model at that time. So showing that these dense models, they work really nice when you have in-domain data. So if you have training data from your domain, they are really good, really nice. But if the task and the domain changes, the performance significantly drops. We also tested a lot of more models, and we compared them. How well do they compare against BM25? So on how many data sets do we see an improvement, and on how many data sets do we see a decrease in performance? So this is like a dense model. Bi-Encoder, the test be the best one we tested. And as we see on 8 data sets, we got an improvement, and on 10 data sets, it was actually worse. And also for other approaches like MSE or DPR, we see quite a performance drop. So DPR was only good on NQ data set, but on all other data sets, it was worse than BM25. However, there are 2 data sets, which two model architectures, which were really strong. The one is BM25 plus a cross-encoder re-ranking. So it performed on most data sets better than BM25, and also the performance gains was the largest on most data sets. And the other one was DocT5 query. I will present these 2 architectures in a minute and also tell you how you can use these models to encode or to transfer knowledge to a Bi-Encoder so they work well out of domain. So first, the cross-encoder. The cross-encoder works in 2 stages. So first, we have first stage retrieval. So you have some queries, some question, and a large document collection. And from the document collection, you retrieve, for example, 100 possible candidates. For the first stage retrieval, you can use any retriever like dense retriever or like BM25 retriever. And then you take these 100 candidates and you send it to a cross-encoder re-ranker. And this gives you the ranked top 10 hits. The cross-encoder takes the query and the document simultaneously into the transformer network. So with a Bi-Encoder, it was separate, the query and independently the document. But here for a cross-encoder, we take them simultaneously into a word network. We have some classification head on top, and it outputs a value between 0 and 1, showing how relevant is the query for the document. And then based on these output of 0 to 1, you can rank the top 10 hits, which are most relevant to your search query. The difference is nicely visualized in this picture between cross-encoder and Bi-Encoders. So as mentioned, for the Bi-Encoders, or also called dense retrievers, we have the query here in yellow and the document here in green independently. So we compute the query. This gives us some embedding. For example, we can use the CLS token or do some mean pooling, and we do it for the document. Also, we get some embedding, and then we can compute the score, which is a dot product or cosine similarity. For cross-attention models or cross-encoders, we concatenate these 2 inputs and pass it through words. So here we do cross-attention between all the query words and all the document words at every layer. And this shows that the cross-encoder is much more computational complex than the dense model or the Bi-Encoder, leading to these better performances, but as I will also present in a minute, have significantly higher computational costs. In our paper Augmented S-BERT, we showed that cross-encoders perform a lot better than Bi-Encoders. So this was on semantic textual similarity, but we also see it for all other tasks. That with the cross-encoder here in red, we see much better performances than the Bi-Encoder. And also especially in low data set settings where we have only few training examples, we see much higher scores for the cross-encoder than we see for the Bi-Encoder. If we compare it on our BIR data set, we see quite a big difference in terms of performance, especially out of domain. So in domain on MS Macro, we see that dense model can improve quite largely. The cross-encoder is a bit better, but the difference is only 0.5 points. So here we see in domain not such a big difference between a dense model and a BM25 plus cross-encoder setup. However, when we go out of domain, like BioAsk, we see quite a performance drop for the dense model. However, we see performance gain with the cross-encoder. And this goes on also for other data sets. So for example, for track COVID, which is on scientific papers on COVID-19, the dense model have never seen COVID-19, so the performance drops quite heavily. However, with the cross-encoder, we see quite a performance gain. So this is like 30 points difference nearly between the dense model and the cross-encoder. On average, on all 18 data sets, the cross-encoder is roughly 14 points NDCG at 10 better than the dense model, which is like really a significant large difference, which every user will notice. The other architecture is doc-to-query. It works in the following way. So you have some input documents, some passages, and you pass them to an encoder-decoder architecture. For example, when you can use T5 for that, and it generates queries which people will likely use or ask, where they are happy to get this document as an answer. And then the original doc-to-query, you concatenate them. So you take your original document, you generate 40 possible queries and documents, queries and questions people could ask about this document. Then you concatenate them and you index them in your search engine using BM25. And then when a user searches for something, you search in the original document and in the predicted queries. And as we see, it also works quite nicely out of domain. So you might ask, why not use cross-encoders or doc-to-query in your search application? So for cross-encoders, they are powerful and good, but they are really slow. So imagine you have a query of 10 tokens and your documents have 240 tokens and you want to re-rank the top 100 documents. So for a Bi-Encoder, you just need to compute the embedding for the query. So let's assume this takes 10 milliseconds. For the cross-encoder, what you do is you concatenate these 10 query tokens with the 240 document tokens for 100 documents. So you have to re-rank 100 times 250 token docs. So this is like an increase of compute by 100. But as transformers have like a squared complexity in the computation. So if the document size is twice as long, you have like 4 times higher complexity in the forward pass. So here we need to score to do a forward pass of 250 token documents and not only of a 10 token query. And doing a forward pass for 250 tokens takes roughly 625 times longer. And as you have to do it for 100 documents, you have an overhead of like 60,000. So using the cross-encoder takes 60,000 times more compute than if you use the Bi-Encoder. So yes, cross-encoder gives you really good search results, but if you want to run search at scale in production, you always want to use a Bi-Encoder because it's a lot more feasible to run these. Doc-to-query is really fast at inference, so at production, because it's just standard BM25 retrieval on your index. However, the indexing is quite slow. For example, in the recommended paper setup, they generate 40 queries per passage. And this question generation is extremely slow and extremely time consuming. So the estimated cost to generate queries for 8 million documents is roughly $750. In comparison, if you compute the dense embeddings for this collection, this costs you less than $1. So doc-to-query is like 750 times more expensive at indexing than a dense model. And if you go to really large collections of 80 million, 800 million, 8 billion documents, this is quite a significant cost for you. However, we can use these techniques and combine them to train a really efficient Bi-Encoder, which I will present in a minute. So from compute complexity, we want to use Bi-Encoders, which create like a dense vector in production because they're efficient at inference, they're efficient at indexing. But how can we adapt them to a new domain? So our goal is to adapt them to a new domain without labeled data. One approach is adaptive pre-training, which I will present. And then I will present the newest work from my research group, which we presented in December, which is on generative pseudo-labeling, GPL, which combines cross-encoders and doc-to-query in a nice way to adapt Bi-encoders to a new domain. So in adaptive pre-training, usually what would have been nice is to have some out-of-the-box model, so some fine-tuned model that is fine-tuned on MS Marco. And it would have been nice if we can do some unsupervised target domain training so that we can take an existing model and adapt it to our specific domain. Sadly, this doesn't work well. So it only improves the performance in some cases. And the improvement is also not so large. So we test a lot of things to get this working. But so far, we failed to do this successfully. Instead, what we can do is adaptive pre-training. So we do pre-training on our target domain, and then we fine-tune on labeled data, for example, from the MS Marco data set. And here we tested different methods for pre-training. The first one is masked language modeling as proposed by Birch, and it works in our experiments. The second one is TSDE, also from my research group, which uses auto-decoders. It also works well. The third approach is inverse closed task. It also works. And then there have been last year some methods proposed to learn unsupervised representations and also pre-training, SimCSE, constructive tension, and condenser, which do not work for this adaptive pre-training. In fact, if you train first with these approaches, the model you get is weaker than if you just would have used the non-fine-tuned, non-domain adapted model. So in masked language modeling, as you're probably familiar, you have some text, you delete some words, and then you do a forward pass through BERT, and then you predict the missing words, so which words have been removed at this position. Inverse closed task is an older technique, which works on the following. So you have some documents, some passage, which consists of multiple sentences. And here at random, you select one sentence. So for example, at random, we select the second sentence and you split it into like one sentence. It's design philosophy, emphasizes code and readability. And you keep the other sentences as a paragraph. Python is a programming language. Python uses significant indentation. And then using this pair, you train Bi-Encoder such that this sentence and the remaining paragraph are close in the vector space. Third approach proposed by my PhD student Keisheng Wang is TSDE, which is based on a denoising autoencoder. So you start with some text and you delete a word randomly in this text. You pass this text through the word encoder, and we add some bottleneck to it. So here we used some pooling. So our goal at the end is to get some good representation of text. So we thought it's a good idea to add a pooling here. So you, for example, you do a mean pooling of all the word embeddings BERT is outputting. And then you take the decoder, or you take this embedding, this pooled embedding, pass it through the BERT decoder, and it reconstructs the text without noise. And we found in our experiments that deleting words had been the best way to add noise to a text. We tested these adaptive pre-training results first on sentence similarity tasks and then on information retrieval tasks, where you have a short query given and want to retrieve a longer paragraph providing the answer. And as mentioned previously, if you first train on the source domain and then train on the target domain, we can see a slight improvement sometimes, but not consistent improvement. So this sadly does not work well. However, if we train first on the target domain with our unsupervised approach, and then on labeled source domain with MS Marco labels, we see that TSDE and mass language model give in both cases really nice improvements, and TSDE giving the best performance. TSDE gives like really nice improvement because we have this bottleneck. So TSDE forces the model to learn good representation of the encoded text, which is then really powerful as a basis to do decoding. ICT also works nice, a bit worse than mass language modeling. And as mentioned, SIMCSE, CD, and CT, they sadly decrease the performance than our out-of-the-box model. Next is a different approach we presented, also Keisheng Wang presented in December, which is on generative pseudo labeling. Here we use a three-step approach. First, for our document collection, we generate queries similar to Dr. Query. Then we do a negative mining using dense retrieval. And then we do pseudo labeling with Cross-Encoder. So the first step is to generate queries. So we have some paragraph from our corpus, like Python is a programming language. Its design philosophy emphasizes code readability. We pass this to a pre-trained T5 model, which generates questions people could ask and which would be happy to get this paragraph as a relevant answer. So one question people could ask is, what is Python? How good is the readability of Python code? And which programming language uses indentation? So this is the first step where you pass all the paragraphs you have from your corpus through T5 to get like different queries people could ask. The next thing is you take these generated queries and you mine documents or negatives in our case from your corpus. So you take which programming language uses indentation, you pass it to your corpus, and it gives you different paragraphs from your collection. So for example, the first hit is you can use indentation to structure your code. Java is a class-based programming language, and C is one of the fastest programming languages available. So this is the second step. And the final step is to pair them, to score them with the cross-encoder. So we take the query we generated, we take the first hit we pass it through the cross-encoder, and we do it for all the documents we are retrieving. And this gives you different scores between -infinity and infinity, how relevant they are. So these are scores which have not been passed through a sigmoid function. So there can be any, so these are the raw logic score, which can be anything between -infinity and infinity. So why do we need the cross-encoder? So two things can happen. So the query generation is not perfect. The T5 system could create like some query, which is not that relevant for the paragraph actually. And also when we mine negative, so if we mine negative, it can happen that we find paragraphs which are really relevant to this question and which would also answer the question. So a previous method, they just said, okay, the positive passage, it's relevant with the generated query, and all the negatives are not relevant. However, it can happen, as mentioned, we have the issue that the generated query is not perfect, and the negatives we retrieve are maybe also quite relevant. So for example, here, in this example, so this is a real example from the data set, we have the positive passage, future contracts are a member of large class of financial assets. So the system generated what is future contract. And then we have different negatives mined. So here we have some negatives mined. They are talking also about future contracts, but they do not define what are future contracts. So it got from the cross-encoder a really low score. Here we have one passage which also defines what future contracts is. So it's simply a contract that requires party A and so on, which also gets a high score from the cross-encoder. And here we have a hard negative. So here talks about future contracts, but it does not define what a future contract is. And And as we see, so here we see that this is actually like a false negative. So this is actually also positive. It gets a score which is really similar to the score of the positive. And if we train now our Bi-Encoder, we use these scores. So we know, okay, the query and the positive should get like a really high score. The query and -2 should get like a really low score. The query and -3 should also get a high score. So how do we use this to train our Bi-Encoder? We do it in the following ways. So we have our query, we have our positive document, and we have the negative document from our mining step. We pass them to the Bi-Encoder individually, and we get like independently different vectors. So we get a vector for the query, we get a vector for the positive, and we get a vector for the negative. Then we compute the dot scores, the dot products between the query and the positive. So we get a score for the positive, and we compute the dot product between the vector for the query and the vector for the negative to get some score for the negative. So this is the scoring from the Bi-Encoder. And now we compute the loss. So we measure what's the distance between the score positive minus score negative. And we compare to what is the score difference between Cross-Encoder positive and Cross-Encoder negative. So here, between this one, so query and positive and query and -2, we want to have a distance of 10 points. While, for example, we're between positive and -3, we just want to have a distance of 2. So the Cross-Encoder actually teaches the Bi-Encoder how far a vector is supposed to be in the vector space. So should they be really close in the vector space, or should they be really far away in the vector space? And the Cross-Encoder tells the Bi-Encoder what's the right position in the vector space for these vectors. How well does it work? So again, we tested on 6 information retrieval tasks. And as we see, so compared to adaptive pre-training with TSDE, we get like another 2 points improvement. And a nice thing is that it can actually be combined with adaptive pre-training. So we first do pre-training on our corpus, then we generate these queries and do GPL, and we get another point improvement. And as we see on the right side, we have like a really nice curve on the training. So the more steps we train, the better the performance. And if you do pre-training first with TSD on your specific corpus, you get also quite a nice performance gain, especially in the beginning, which of course narrows down the more steps you train. So in conclusion, dense models, they have issues with unknown words. So if it has never seen a word in pre-training and in fine-tuning, does not know how to present the word in the vector space. So is this the newest cryptocurrency, the newest transformer model, or the newest company, or some error code from some program? So these words are really hard for dense models. Pre-training on target, and then you can do fine-tuning on your source domain, for example, on MS Macro. It can help, but it does not fully solve the issue. Also, it has quite high computational overhead. So pre-training is expensive, and also training on your source domain where you have the labels is extremely expensive, especially when you have a lot of the labels available in the source domain. Generative pseudo labeling it gives like a nice performance increase without the need of labeled data. So we just generate our data using Dr. Query, but still the computational overhead is still kind of high. And so it's roughly 1 day on a single V100 GPU. So that's not too expensive, but nothing which you can just run in 5 minutes. And efficient and continual domain adaptation is still an open question mark. So these approaches work in batches, but you cannot apply them yet on a continual basis where you get a certain number of documents on every day, which would be really nice if you could update your models as soon as it detects like a new document and incorporates this knowledge into the corpus. Thank you very much for listening. The code for GPL is available. It's hosted on gpl.esprit.net. And the usage of GPL is really simple, and it gives you a nice improvement for dense models for a domain-specific corpus.